Okay, so this is a series we're going to discuss. First of all, you have to answer the question whether it's convergent or divergent. Okay, if it's convergent, then you have to prove that. If it's divergent, you also have to prove that. Now, the nth term is n over n plus 1, and this is clearly convergent to 1 as n approaches infinity. Okay, so the sequence is convergent, okay, but the series is divergent. Okay, the sum of all those terms is divergent. Well, sounds obvious because you have many terms very close to 1, add them together. Infinite many terms, of course, the sum is getting larger and larger, right? What you have to say that the series have to say that because we don't know which one you're talking about, right? So the series is divergent by the test for divergence. That's enough. The evidence is the limit of n is going to be what? You provide this as evidence, then you quote the theorem or test to get conclusion. It is divergent. Now, what is the test for divergence? The test for divergence says that if a series is convergent, then the limit of the nth term is 0. Okay. But well, this is about convergence, right? No, it's about divergence. If the series is convergent, yeah, then the nth term has a limit, which is 0. Now, what the evidence you provide is the nth term, the limit, is not going to be 0. So the series is divergent. Because if it's convergent, then the limit must be 0, right? That's it. So this is the correct argument. Okay. So this is this part is test of convergence. Yeah, this is a test for convergence. Even I even mentioned that, a test for convergence. Okay. Okay. The second one, okay, it is going to be 3 to the power n minus 1 over 4 to the n. Okay. Question is it convergent or divergent? Prove your claim. Okay. Now in this case, right, the nth term, you can look at nth term converging to 0. Okay, so this is actually is convergent. Now what you have to give some information, evidence, right? Then you quote the theorem. The theorem maybe you can call the theorem for on the geometry series, maybe like that. Okay, this is a geometry series. Okay, you have to indicate this is geometry series, and you can even find the sum. Okay, so the geometry series. Let's look at the finite sum. Now, if you just want to prove it's convergent, you don't need that. Okay, so this is going to be the first term will be 1 over 4, right? The second term 3 over 4 squared, and the last term 3 to the power m, 4 to the m. Okay. You can take the common fact out, which is going to be 1/4. Okay, it's 1 plus 3 over 4 and 3 over 4 squared and 3 over 4 to the power n minus 1. Okay. Yeah, you can compute it directly. So that's going to be 1/4 according to, yeah, there's a formula there. It's 3 over 4 to the power m minus 3 over 4. Okay. So when m goes when m goes to infinity, 3/4 to the power m approaches 0. Okay, so that approaches quarter times 1 minus 0, 1/3/4. Okay, let's simplify it. It's going to be just 1, right? Just 1. So the answer is 1. Okay, that is the limit. So therefore, you not only prove it's convergent, you also prove that it's going to be equal to 1. Okay, this is one of the proofs. Okay, another proof, you don't need to go through all the arguments, repeating the argument we did for the geometry series. All you have to do is, okay, look at this series, okay? And this is a geometry series because 3 to the n minus 1 over 4 to the n. You know, the geometry series, the standard geometry series is going to be in the form ar to the n, okay? So this is a geometry series. Well, you can also start from any number n, from capital N. Okay, so if you write in this form, then I think you just express it. It's like 1/3, 3/4 to the power n. So it's geometry series. Okay, it is a geometry series with r equals 3/4, and which is less than 1. Okay, then therefore it's less than 1. We know for geometry series we have a theorem there. Then it is convergent. Okay, now in this case, something we maybe don't want to mention because you already mentioned geometry series, so it implies that you already know the theorem. Otherwise, you just say that by the theorem on geometric series. Okay, you can say that geometric series. Okay, there's a theorem says that the geometric series is convergent if only if the absolute value r less than 1. Now your r is going to be 3/4. So you don't need to go through the above arguments here. Okay? Yeah, it's not necessary. Unless I ask you to find the sum. If you just ask whether it's convergent, then you don't need that. Okay? All right, the third problem is this, 1/n. This is called harmonic series. Okay? Harmonic series, we know it's divergent. Okay? But its proof is very technical. It's given in the book. I did not mention that. But is there any other way to show this is a divergent? Okay, divergent means I want to prove that divergence means the limit n from 1 to n goes to infinity as m approaches infinity, right? That means, okay? So can you prove this approaches infinity? Okay. We can, the simple observation is that, okay, we want to get a lower bound, right? 1/n, okay, is going to be integral from 0 to 1/n should be greater than equal to n to the n plus 1. Do you agree? Because 1/n is greater than equal to 1/x if x is larger than equal to n. Okay, so this is a key observation. Okay, then sigma m n start from 1. Yeah, I give you another proof. Okay, why this is trivial? Because 1/n is greater than 1/x for x in the interval from n to the n plus 1. Okay, yeah. Then you integrate on both sides from n to the n plus 1. The left hand side is still 1/n. The right hand side is the integral. So it's going to be Okay, now if you write down the detail, what do you get? You get 1 to the 2 1 over x dx, and from 2 to 3 1 over x dx, right? All the way to from m to the m plus 1 1 over x dx. Then because it's integral, interesting, you can all put together, right? Integral. So it's actually it's just simply from 1 to the m plus 1, right? And you can evaluate this integral. The integral will be natural log of x, evaluate to the, right? And natural log of 1 is 0, so it's just natural log of m plus 1. So the sum, the partial sum, 1 over n, is greater than or equal to natural log of m plus 1. Okay? Yeah, you understand that, but it's not easy to find this idea. Understand? You understand in mathematics, yeah. In many cases, you understand how do the people get prove this statement, but it's not easy to find this idea. Okay. But it's hard to tell why this person found this idea and why I cannot. Cannot because I'm stupid, because there are various reasons. Okay. And it's like yeah, it's hard to tell. Okay. But for majority of people, if properly training from the childhood, I strongly believe that no matter you are female or male, and you can always get a PhD in mathematics. Okay. But for some reason, you couldn't, even you want to just, a certain period of time, you're supposed to learn this stuff, but you didn't. Okay. Just like these days, kids are so busy with the iPad, iPhone, playing games, and they waste a lot of time. It's hard to control that. Honestly, someday when you have a kids, you're busy. Most of the time, just say, play with my cell phone, play with an iPad, and they enjoy that. Okay, then let's keep a lot of time. Yeah, they're supposed to learn things. Okay, anyway, so this is a lower bound, right? And clearly this goes to infinity as m approaches infinity, right? So therefore, it's a lower bound, but lower bound is greater than or equal to m plus 1. Okay, they're not big difference actually. The upper bound is also natural log of something, but it's almost, yeah, we can get a very good estimate on this harmonic function. Okay, so this is going to be so therefore this pushes the limit n approaches infinity. Okay, so that's why it's divergent. See, the proof is just use the integral. Now this is what we're going to study today. Integral. Okay, integral. It's called integral test. Okay, let me state the theorem. Okay, the theorem says that if the function is continuous, okay, we assume that f is continuous, okay, on some interval from capital N to infinity, satisfying the following two conditions: f of x is positive, 2, f of x approaches 0. Okay, not approaching, decreasing. We need a decreasing. If it's not approaching 0, definitely it's divergent. Okay, so don't worry about that. So it's decreasing. Okay. Okay. Then for n equals f of n, okay, this convergence, okay, is equivalent to the convergence of the integral. It's converging if only if the integral from n to infinity, f of x is converging. So there's no difference between those two, but that you can also estimate. Okay, so estimate you can get the estimate. Why this is true more precisely, you have the following. Okay, this is a we can have we can we can have the following coordinate. This integral is greater than or equal to n from capital N and less than or equal to n from limit. Right? So this last inequality really tells you whether tells you the equivalence of the two convergence. Okay, you can see that if this is a finite, that means it's a finite. Okay, so this is convergent in product. Then if this is a finite, if this is convergent implies this. That is fine. So that's why. But you can also get a very good estimate using the encoding. Now the estimate you can also write to exist. N from capital N, and right. I want to get lower bound. Lower bound is still the same. The upper bound actually is going to be from N plus AN. Okay, so this is another way to this two inequalities are same. Okay, let's see. How do I get the lower bound is greater than that? So that comes from here. So how can I get this one? This actually comes from here. Just a sub n to both sides. And this side you get this, and then here you get this. Okay. So yeah. So proof is similar to the argument I just gave to you for the harmonic functions. Okay. The key idea is the following, because the function is decreasing. So the proof, I'm not going to the key idea, the key inequality is as follows. F of x is greater than or equal to a to the sub n plus 1, sorry, n plus less than or equal to n for x between n and n plus 1. So you integrate, right? You integrate from n to the n plus 1, f of x dx, and then this side is an, the other side is an plus 1. Okay? Yeah. Then you add it together. Okay? When you add it together, sigma n from capital N to n. This is also, right? And the other side is n from capital N, a n plus 1 to n, right? But the one in the middle, well, all those integrals can put together. So this is actually from capital N to n plus 1 f of x dx. Okay, right? Then after you pass the limit, you get the above estimate. Okay. So you can let n go to infinity, then you get the result you want. So so let m approaches infinity. This side okay. So that's all how to get. Then you see which one. Yeah, whenever one of them is convergent and the other one is convergent. All right, so let's take a look at the following series. N start to 1 here, n to the power p. Okay, I want to see when, for what variable p this is convergent. Okay, and we assume that p is greater than 0. Okay, if it's not greater than 0, it's divergent, it's obvious. All right, so let's look at this function. And obviously the function n, the nth term is n to the power p, which is f of n. And what is f of x? F of x is 1 over x to the power p. Right? So this function, when p is greater than 0, this function continues. Also, this function, yeah, f of x is greater than 0. F of x is decreasing. That this function meets the requirement in the theorem. Okay, therefore, the convergence is of those two. One is the integral, the one is the series, are equivalent. Okay. So we get capital N is right. What do we get? We get, if I use a second inequality, if I use this inequality, no, the inequality above, right? If I use this inequality, and you will see that capital N is 1, right? So what I get here is sigma n from 1 to 1 over np is less than equal to the integral from 1 to infinity, 1 over x p dx, plus the first term is just 1 over 1 to the power p, and greater than equal to. So we not only know the convergence, we can even estimate. Okay? Clearly, this integral of the divergence, which is less than equal to 1, right? So clearly, yeah, we have the following integral property. This is going to be positive infinity if p is greater less than equal to 1. Okay, and what happens if p is greater than 1? If p is greater than 1, I think it's 1 over p minus 1. Yeah. Okay, it's finite. Right? It is finite. The idea is that it's right. This is a function. The entire derivative of the function is like that, and then it goes to infinity, right? So let's check. Okay, and then when x approaches infinity, p is greater than 1, so this approaches 0. So you only get negative 1 over 1 minus p, which is 1 over 1 p minus 1. Okay, so this we already know for the integral. So we put back. Okay, so if both sides are infinite, then definitely it's infinite. So this is we know that we conclude that if p is less than 1, okay, then this is divergent. Okay. Now, if p is greater than 1, it is convergent. Not only convergent, I can even tell the value. I can get the estimate. This is less than equal to p minus 1 plus 1, greater than equal to p minus 1. So you get very good estimate. Okay. Not only, yeah, convergent, we can get even estimate. Of course, when p very close to 1, the estimate, well, the estimate is pretty good. The gap, the error is less than 1, at least, right? The error is less than 1. When p is very large, this is not a good estimate. When p is very large, you see the error is 1, then the value itself is also very small, right? Yeah, when p is very large, it's not a good estimate. When p is close to 1, it's good estimate, actually. Yeah, okay. When p is small, close to 1, it's good estimate because of this series. The series is between two very large numbers. And these two large numbers, the gap is 1. Compared to two large numbers, the gap is very small. Okay. Anyway, this is a good estimate. And this we call the, in the future, we're going to call the p-series test, okay? So we get the p-series test, okay? It says that this series from capital N, 1 over p, right? Okay, is convergent if and only if p is greater than or equal to 1. Okay? If p is less than 1, it's divergent. Less than or equal to 1. When p equals 1, this is this, yeah. When p equals 1, this harmonic series it is also divergent. Okay, we will use that, okay, in the next class to prove, yeah, something is convergent. Okay, something is convergent. Okay, so let's take a look at the next problem. How about this series? Okay, so this is going to be, yeah, just n squared plus. Okay, so I think this series is convergent. Why? This is almost equal to 1 over n squared, right? Now later on, we're going to study comparison test. So you can compare with, so here, yeah, let me show you the ideas of a comparison test. Because comparison test is pretty obvious. First of all, this series either infinity or finite, okay? If it's finite, we call it convergent. Why it's always? Because it's increasing the partial sum, okay? The partial sum. Every term is positive, it's increasing, right? As long as it has a finite upper bound, then it's convergent, okay? Right? It's increasing every time we get a positive number, okay? So in order to prove, then I guess this is convergent. Why it's convergent? Just because it's almost, right? N equals n squared plus 1 is almost equal to 1 over n squared. Okay, so I guess this, because I know this is a convergent. So I can use that to prove this this series is convergent. So how can I do that? It's very simple. It is going to be less than equal to, right? Less than equal to n over n squared plus 1, because we drop 1 in the denominator, make it larger. But this already using this above estimate, right? Okay. So this is already less than equal to, of course, when n goes to infinity, right? And more terms add on, and this is less than equal to when p. I can not only show this is finite, I can even show that this is less than 2. Okay, it is less than 2. All right, so the upper bound is 2, therefore it has a limit. Okay, there's upper bound. So therefore, this is a convergent. Okay, and the limit is always less than equal to. Okay, I can get that. Okay, so not only we get additional information, not only convergent, we also prove this less than equal to. This comes from the limit, but suppose we don't know this comparison argument. Okay? We are in a section called integral test. Maybe we can use that to prove it's convergent to the estimate. Okay, so n equals n squared plus 1, which is equal to f of n, and my f of x equals x squared plus 1. So this is a positive and a decreasing. So as long as you can prove this integral is convergent, then the integral, right? If this is convergent, if we can even estimate the value, I can get the result for the series. Okay, so the question is, what is that? It's finite or infinity? Okay, but above argument shows that we have this estimate right? We have this capital N here in this, right? Or you can use this. Where's my estimate? Yeah, I prefer use this estimate, right? Okay, using this estimate. So let me write down the estimate. Okay, so sigma n start from 1 to the n squared plus 1 is less than or equal to the integral from 1 to infinity x squared plus 1 dx plus the first term when n equals 1, that's 1/2, greater than integral. So we can get a very good estimate. If this integral is finite, then the gap between those two bounds is just 1/2. That's pretty good. Okay. Are we able to evaluate this integral? Yes, we can. Okay. This is going to be the limit b approaches infinity, and the antiderivative of 1 over x squared plus 1 is going to be arctangent x. Okay, arctangent x. And arctangent b approaches pi over 2 if b approaches infinity. Okay, so this is going to be arctangent b minus arctangent 1. Arctangent 1 is going to be equal to pi over 4. But arctangent infinity is pi over 2. So it's pi over 2 minus pi over 4, which is pi over 4. Okay, we can even get the exact value. Great. So what we get is not only convergence of this, we can even get estimate. Great. We can tell this series is within those two numbers. However, is smaller than 1. Okay. Yeah, however, is smaller than 1. So the estimate is not that great. There's a gap is, yeah, it's pretty large. It's 1/2. But we know that this one is between those two numbers. And sometimes we do need to estimate. Okay, so the series, the value of the series. Okay, and we're lucky we can evaluate the integral 1 over x squared plus 1. In some cases you cannot. Okay, in some cases you cannot. All right, our next problem is going to be this. Can you make a conjecture? How can you guess this convergent divergence? Okay. Now I'm not asking you to act like a lawyer. Okay, find evidence and prove it's convergent, and using some test. I'm just asking like a jury, sitting there, you watch it. Can you tell? Right? This is a convergent divergence. Okay, get some idea. Okay? Of course, if you do more exercise, and you get a better feeling about the series. Now, we have a p-series test. Okay. This is this only have 2 results. If p is less than or equal 1, if p, then it's going to be p minus 1 if p is greater than 1, right? So n to the power p. I want to compare. See, the natural log, okay, it's greater than n, clear, right? Of course, n should be too large, okay, because natural log of 2 is still smaller than 1. So we just assume n greater than 3, okay? Yeah. And this is going to be less than, okay, less than any numbers, 1 plus action, okay? But then I have to say this will have to be larger than very large number because yeah, 3 is not enough. So it depends on the action we choose. So, but it's still harder to tell whether this is the version or that. Okay? Because it's between the string. The lower bound is n. One of n is this series is divergent. Other side is convergent. So it's still between divergence and convergence. Okay. So it's it is hard to tell. Okay. 1 of an h log n is less than 1 of n, greater than. Okay. And you put a sigma on both sides. One side is finite, the other side is infinite, so you cannot tell any conclusion. Okay. Using this comparison, you are not able to jump to conclusion it's divergent because the left-hand side is convergent, the right-hand side is divergent. Right-hand side is harmonic series. So if some number is between finite and the infinity, you cannot tell this is finite. Could be infinity. Okay, inconclusive using this kind of comparison. So you have no choice except let's try use the integral test to see. Okay, I let f of x to be 1 of x natural log of x. And I think it's clearly this is going to be, first of all, positive, okay, on the interval from 2 to infinity. This is a positive, and this is clearly decreasing. Why is it decreasing? Because denominator is increasing, right? It's obvious, right? So I'm going to integrate from 2 to infinity, f of x dx. Okay. Right, so can we integrate this? Answer is yes. Right, so this is going to be the limit as b approaches infinity from 2 to b x natural x dx. Okay, so the entire derivative, I cannot get the entire derivative directly, so I have to do some computation. So I use a substitution. U is going to be natural log of x. So du will be 1 of x dx. Okay. So dx over x is going to be du. So the answer will be gives u du. Okay. Oh, that's good. So we can evaluate the integral. Okay. It's going to be natural log of u. Okay. It's going to be natural log of natural log of x. All right. So you can put the constant here. This is a general formula. Okay, you use that to evaluate the above integral from 2 to b. It's going to be entire derivative b minus, okay. And clearly it approaches infinity because natural log of b approaches infinity. So natural log of b approaches infinity. So clearly it's going to be approaches infinity. So that means it's divergent. Okay. So that means it's going to be divergent. That implies right. You see, it's not easy to do the argument like that, okay? So take it serious, okay? I don't want you to your scores drops. You know, you already got lower scores maybe on test 1. Okay, take it serious. If I don't see you here, okay, and you have to convince me someday that I'm very serious about this course and how to do that, right? The only way you can prove that you are online, watch my videos, okay? If not, then okay, sometimes I do not post the videos. Nobody sends an email to do that to this. Probably you're not watching because you really watch it. You already say, hi, where's our video? Okay, right? So I silent. Nobody sent email. So yeah. Anyway, I wish you do well in this course. Of course, we can move on to the next class, 262. Okay, this is this is it's really pure mathematics. It cannot just use a formula to evaluate integrals. You have to really find the reasons, give me very good argument about it. Okay, so how to do this problem? You look at that, right? It's harder to get any conclusion using comparison. Okay, so I was trying to do that, and failed because we're going to learn comparison test. Yeah, so it's not working. So then I say, okay, let's try and use a integral test to find the corresponding function, and then you look at corresponding function. Yeah, it's decreasing, it's positive. So then just look at the the integral of the function. Then you have to evaluate the integral. Okay, the substitution. The integral is this improper integral is divergent. So that's why it's a series divergent. Now you have to say that by the integral test. Okay, so do not try to save time because you have to give a complete argument so the people can understand. Okay, some students just even ignore that without write down the series, just say divergent. That's it. So what is it? Which one is divergent? You're talking about the integral divergent or the series, and without mentioning the integral test, right? I was asking to prove this series divergent. Then you begin with a function without saying anything. Then you show that the integral is divergent. Then you just say divergent. Okay, that's the incomplete solution. Why? Even you haven't mentioned even the series yet, right? You're doing something different, problems. You're working on the integral. Then you say it's obvious, it's integral, but you did not say that, right? Okay. You just work on another complete different problem, integral, instead of a series. And you only prove that integral is divergent. Is there any connection to the original problem? You did not say that. See? So that's called incomplete solution. You cannot say it's obvious. We are taking calculus too. You know that I'm talking about the integral test, but no, I just assume I don't know. Okay, you have to show this work to somebody else to see if they know what you're talking about. So you have to say this is a very important step. Okay, don't skip that. All right. All right, so the next problem is this problem number 22. So let's finish that quickly. Without the natural log, I know this is a series. Okay, this series is convergent. This is a convergent, and I have to say that by the P series test. Okay, but this cannot help you to answer the question. Okay, because the numerator is getting large. Okay. In natural log of n, I want to tell you this is going to be still convergent. The reason is natural log of n compared to n is really, small. Okay, it's always less than any small epsilon. Okay, for large n, so that epsilon is positive. Okay, that helped me to get to the conclusion it's convergent. But this is a comparison test. Okay. And the reason is, yes, natural log of n is getting larger and larger, but it's not that large enough. So natural log of n over n squared is going to be less than n epsilon, n squared is going to be n the 2 minus epsilon. But 2 minus epsilon, as long as it's larger than 1, it's convergent. Okay? So but this will, we'll discuss this later, because this is not what I want to talk about. But from here, I can tell this is convergent. Okay, but I'm trying to find the proof. Okay, so I can let the action to be 1/2, for example, right? Then 2 minus 1/2 is still greater than 1. So this is convergent. So this is idea will be used for comparison test. We are going to use an integral test to prove this, okay, if possible. So this is going to be f of n. My function is going to be natural log of x over x squared. So this is this function is not obvious, it's decreasing, right? So this function is not obvious, but it's positive on the interval, I think from 2 to infinity, okay? Yeah, it's positive, clear. Yeah, natural log of 2 is positive, okay? Natural log of 1 is 0. So this is positive. But decreasing is not trivial. You have to prove that, okay? I think it's decreasing. Why? Because natural log of x, it grows, but it grows slow. The denominator grows faster. So the quotient decreases. That I have to say that, right? You cannot say it's obvious. Okay, the best way to do is just prove that the limit, the derivative is going to be negative. Okay, so you find the derivative, so you get x to the 4th power, and this is a x squared, the derivative of natural log 1 of x minus natural log x, and then derivative of x. Okay, and after you simplify the x, you get 1 minus 2 natural log x. Okay, and this I want to make sure it's less than 0. So when, right? When natural log of x is greater than 1/2. Okay, this is the same as, yeah, this is same as x greater than e to the 1/2. Okay, it's some number. That's okay. And e to the square root of e. Square root e is less than 2. Okay, square root e is less than 2. Why square root e is less than 2? Square root e is less than square root 4, which is 2. Okay, so guarantee if x is greater than 2, if x is greater than 2, then natural log x is greater than 1/2. Okay, so anyway, this is for x greater than or equal to 2. That's guaranteed. Okay, but that's probably x greater than or equal to any large number. It's enough. Okay, but this is so decreasing. So therefore, f of x is decreasing on the interval. Then you can apply the integral test to solve the problem. So the integral test, right? Let's look at this. Are we able to evaluate this integral? This is a problem. Are we able to evaluate this integral? Okay. Can we find the antiderivative of the function? You have to find the antiderivative of the function. Okay. Okay. So let's look at, yeah. So we have to figure out this. If it is finite, then the corresponding series is finite, convergent. Okay. So the question is, can we prove it's convergent? Okay. So the antiderivative, a typical problem here is x. How do you evaluate this integral, right? That's a good question. You have to get rid of, you cannot use a substitution. Can you use a substitution? Let u to be natural log x. It does not work. Okay. So use integration by parts. So you differentiate natural log x eventually. Okay, that's what's dv. That's u. When you switch it, du, get rid of, natural log is gone. But then what is a v? V is going to be x to the -1, negative. When you differentiate, you get the x to the -2. Okay, so it's uv minus v du. Okay, u is going to be natural log of x. V is negative x to the negative 1 minus negative x to the negative 1. And net du is going to be 1 of x. Okay. So the entire derivative is still going to be, okay, it's going to be this. So we get, let me summarize. Okay, we get this. So this is the entire derivative of the function. Okay, so now I'm going to go back to the this function, right? So it's going to be okay. So the first term will be negative, and natural log of b plus 1 over b minus the plus 2 natural log of 2 plus 1. Okay. Clearly, this approaches finite number. Why? Because the first term, this moves faster than that, so that's why I approach it here. So this approaches. Let me change the order. Okay. B approaches infinity. Okay. So yeah. So this integral is convergent. Okay. This integral is convergent, then we know that this is convergent. Actually, we can even get an estimate. Okay. This is convergent by the integral test. Okay. And if you want to get the estimate, you get the integral of this, it's going to be 1 plus natural log of 2, and the plus the first term. First term is 4 natural log of 2, okay? And the greater than, yeah, greater than this. So it's pretty good estimate, right? If you want to get an estimate. So don't forget to put an estimate there when you do the homework. Okay, let's stop here.